All right, so last week we talked about machine learning, which is basically computers automatically developing algorithms by seeing data. So we show a machine learning program, data examples, and the answers, and it generates equations, coefficients, and that sort of thing that models that relationship basically between all of the different features, which is the input data, and the target, which is the thing that we're trying to predict. We saw a couple of different algorithms. We saw a couple different kinds: supervised, unsupervised, semi-supervised. We did a classification task, and we did a regression task. So classification, just predicting which type of thing something is, and then regression, predicting continuous values like temperature or cost or something like that. Deep learning is really just a different kind of machine learning. So you can do classification, you can do regression, you can do supervised or unsupervised learning with deep learning approaches. It's really just it's an approach that allows us to tackle different kinds of problems because it works differently. So we're going to talk about some definitions and an introduction to neural networks. Talks about some of the different predominant neural network architectures and then how they're trained. And so some of the concepts will be maybe a little more sophisticated than we'll test for in this class, but they're important kind of foundational concepts. So I'll call out some of the areas that won't be tested, but it's important to understand kind of the basics of how this type of machine learning works and what it does. So some definitions. So I showed this last week whenever I got the question, basically to delineate machine learning and deep learning. So all AI involves computers learning and taking action, and so AI really could predate machine learning. It's early chess applications were not really automated algorithms. They were kind of conditional logic type algorithms about board states and things like that. Machine learning involves using algorithms to parse and make a determination or prediction, and so we saw that. We basically split our data up into train and test, and we showed the train data to the algorithm, let it make some inferences, let it develop its coefficients, or however the decision trees or however the algorithm worked, and then tested it on the test data, and then we could provide new data to make predictions. And so that's machine learning. Basically, the algorithm automatically parses the data and provides a prediction, and then we can take action based on that. And then deep learning involves artificial neural networks. And so it's a specific kind of machine learning, which is a specific kind of artificial intelligence. And so we're going to talk about functionally how does deep learning work? What are artificial neural networks? And how do they learn, so to speak? So an artificial neural network is roughly inspired by the human brain's interconnected neurons. So basically we have, instead of a few algorithms, we have thousands or even millions that kind of work together to form an overall machine learning architecture. So it's this dense interconnected set of equations and matrices that all automatically tune themselves to represent the data. So frequently image recognition, neural networks are used for that, and so the neurons all get programmed in such a way to detect relationships between pixels and things like that, and we'll talk about that in a little more detail. Millions of examples are fed into the network to teach it to recognize patterns. And so one of the distinguishing characteristics of neural networks is they can profitably learn from many more data sets, or many much larger data sets, than traditional machine learning algorithms. And so neural networks tend to really excel when you have at least hundreds of thousands, if not millions, of training examples. They tend to be overkill whenever you're working with thousands or tens of thousands of training examples. For really small data sets that only have a few rows, it tends to be kind of like using a sledgehammer to drive a nail. It works, but it's not an ideal solution, and you also tend to have problems with overfitting, which, if you remember, is where the algorithm basically sees a signal that is not there. Neural networks excel at this. If your data set is too small and your neural network is too large, they will see all kinds of patterns in the data that aren't really there, and overfit the data. So basically try to give a very high accuracy for the trained data, but you would have a very low accuracy for the test data. Deep neural networks can extract high-level features from raw inputs, and so we can provide voice or images or even text like words to a neural network, and it will the textual neural networks understand sentence structure. They understand parts of speech. Obviously, the ones working on voice data understand words. They understand intonation, all kinds of different things. And so so we can take data that's very complex and very and sometimes messy, and feed it and prepare it and feed it to neural networks, and they can parse it and extract the high-level features, like putting shapes together to recognize a car. Right, a car is made of several different shapes, and so a neural network basically generates that high-level representation of a car from all the lower level, like circles and squares and boxes that make it up. And then finally, networks automatically learn abstract representations by continuously tuning and optimizing neuron weights. So we're going to talk about what that really means. We're going to unpack that in a couple slides, but basically it's what I was just talking about, where we develop an understanding of stop signs or cars or anything based on decomposing it into simpler shapes or simpler colors and things like that. So use cases. So artificial neural networks, or ANNs, are ideal for use cases involving lots of data. So like I said, hundreds of thousands or more samples usually. Many features. So artificial neural networks are usually used for very wide tables where you have hundreds or maybe thousands of columns. They can work very well with sparse data depending on the architecture. Images or videos, I talked about this, picture, video classification and categorization. Neural networks excel at this. Traditional machine learning approaches are terrible at this. And then series data, so ordered data sets like time series, text, anything that has an ordered component to it is usually pretty good candidate for a neural network. So like health data, like monitor readings for heart rates and things like that. Neural networks are frequently used to try to correlate health readings to look for symptoms that can be correlated and indicate something like sepsis or something like that. Neural networks tend to excel at that and be better than traditional machine learning approaches. So how do they work? So I talked about an artificial neural network being, on this slide here on slide 4. I show this sort of dense connection over here on the side. And in this case, all of these are neurons that are being connected together by weights. And so we're going to take a look at just how one of those would work, right? One out of those, however many is on that diagram, 9. So at their simplest, one artificial neural network or neuron takes inputs, it applies weights to those inputs and a step function. So these are just nonlinear functions. It could be as simple as the output of the function equals 1 if the weighted sum of all its inputs are less than or equal to 1, or greater than or equal to 1. And so in this case, if all of these weighted inputs were greater than or equal to 1, this is 1, and if not, then it's 0. That could be a step function. And so this is an example of a linear threshold unit. The definition of that is not important to memorize. That's just the terminology for it. An LTU is that step function where the output is 1 if the weighted sum of the inputs is greater than or equal to 1. It's similar to a logistic regression classifier, or linear SVM. And so at the end of the day, basically what it does is it takes all these inputs. So these 3 would be features. So if you think of the housing data, this could be number of bedrooms, this could be the population column, and this could be the square feet column, right? And so the number of X here, the inputs, is equal to the number of features. So if you have 3 features, that's what this one looks like right here, right? If we had the iris data, there'd be 4 of these, right? There'd be the sepal length, the sepal width, the petal length, and the petal width. And each of those would get inputted to the neuron. And so the way this works is each of the input columns, or each of those features, gets multiplied by a weight. And this weight could be anything. It's usually 0 through 1. And it's actually part of the algorithm that gets optimized. And so what the algorithm basically finds is what is the weight for this first column, maybe it's sepal length, that whenever I put it into this neuron, gives me the best answer, right? In this case, we'd be trying to predict which species it is. So maybe if I tune this weight so that it's 0.05 times the sepal length, whenever it comes in here and gets summed with these other weights, maybe that gives me the answer better than 0.1, right? And so ultimately the algorithm just continually refines these weights, which literally get multiplied against the input. In this case, they get summed and checked to see if the sum is greater than or equal to 1, and then we output a 1, right? And so what do we tune? In this case, we only tune these 3, or in the iris example, it'd be 4 weights. And that's at the simplest how an artificial neural network works, is it's a bunch of weights against the inputs. They go through a function, which we can select a number of different functions. The LTU is just the simplest. And then we get an output. In this case, we'd get a 0 or 1, which would be a classification problem. So how would we do a classification for 3 types? So in this case, I get a 0 or 1, right? But that doesn't help me, because what I really need to know is which of 3 species is it. I don't need a 0 or 1. I need to know, is it species 0, 1, or 2, right? For the iris problem. And so in this case, we'd use something more like this. We use a perceptron, which can categorize items into different binary classes. This example here would output 3 classes. This is a multi-output classifier. So what this means is, let's think about it in the context of that iris problem, right? So we have 4 inputs. So in this case, we'd have one more input layer, right? We'd have x1, 2, 3, and 4 for the different features. We had 4 features for that problem. We would have 3 outputs, one for each species, right? There was a Virginica, and I don't remember the other 2, right? But there are 3 species represented by 0, 1, or 2. In this case, each of these would be basically assigned a species. So this first one would be 0, this one would be 1, and this one would be 2. And so what we do is we take all of these lines, which in this case represent weights. So x3, this third feature, has a weight to every one of these outputs. You can see it has a connection to each of the output layers. So does x2, so does x1. And so at the end of the day, we take all of these weights and we tune them. And so if a wider sepal is more indicative of the 0th class, or the Virginica species, then this weight would probably be higher, right? And if a smaller one is more indicative of the last species, this weight would probably be lower. And so each of these weights gets tuned specifically based on its relationship to which species of iris it is. So if it's a wider sepal indicates 1, the weight's probably going to be higher. If a more narrow sepal indicates a different species, the weight for that specific species will probably be lower. And at the end of the day, each of these output is 0 or 1. So if this outputs a 1, it means that the algorithm has guessed that it's the Virginica species. If this one outputs a 1, we're guessing that it's the first, and then this one the second, right? And there are some approaches, because you could ask the question, well, what if 2 of these output a 1, or what if all 3 of them output a 1? And there are some algorithms that basically just take the highest confidence, or the highest output. And so since we have these weights coming in, we can sum the weights, and then we can use a different step function to figure out, well, which one does the neural network think it most likely is, right? And we can talk about that here in a couple slides. All right, and so at the end of the day, we've just taken this simple architecture, right, and we've just multiplied it by 3, right? So we just have these 3 output, and then we have what's called a bias neuron, and this is always 1, and it has its own weights, just so that we always kind of have at least something to multiply against. We never get all the way to 0. Biases are very common, and they just kind of represent things outside our features. So it's just standing in there, and it literally is 1, and it just has a weights matrix that gets multiplied times each of these, depending on basically kind of like a fudge vector, I guess you could say. All right, deep neural networks. And so we can take this right here, this perceptron that we saw, where it's only the input layer and the output layer, and we look at these outputs to see which species the algorithm guessed, and we can stack another one right on top. And so you can see here we have our inputs. They go to this, what's called a hidden layer, and each is connected to each. So these are called dense neural networks, where basically everything is connected to everything from layer to layer. You can see the inputs don't skip and go straight to this output layer. They all connect to everything in the layer above them, and then everything in that layer connects to the next one. So we can stack these LTUs to make more sophisticated networks. Each layer between the input and output are called hidden layers, and we can have an arbitrarily large number of hidden layers. And so we could have 5 hidden layers, right? We could just keep stacking these on top of each other to add more and more layers. And some neural networks, especially for image recognition, are literally hundreds of layers. I think one of the pretty common ones, ResNet for image recognition, is like 152 layers deep. And in that architecture, it is more sophisticated, where some layers skip and communicate to other layers, but that, like I said, tends to be a little more sophisticated of a pattern, and we're not going to use that in this class. But at the end of the day, each of these is a weights matrix that gets connected to each of the other neurons, and then we have another set of weights from this hidden layer to the output layer. And why would we do this? Well, at the end of the day, stacking more layers on top is how we generally get the network to understand more complex concepts. So that's why it's very common for image recognition or for video recognition to have very deep layers, is because that's how they understand the connection between shapes and concepts. For pretty simple problems like the iris classification problem, we really wouldn't need any hidden layers. We don't have a whole lot of samples, and we don't have a whole lot of features, so it's a pretty simple problem. But so at the end of the day, we can stack layers, and these layers all have weights, and these weights all get tuned to represent the data or to represent what we're trying to predict. Oops, went backwards. So neural network steps. So how do we do it? So we prepare the data, just like with machine learning. We have to normalize the data. So normalizing the data is very important with neural networks. Generally, it's even more important than with traditional machine learning. Because of the way the linear algebra works, you can get a huge increase in accuracy just by scaling and normalizing the data. We also have to shape the data, so we have to make sure the data has the right number of columns and it's not missing any values, just like we did for other machine learning tasks. So this is no different than what we saw last week. We have to build the network, so the architecture or the type of the network, the type of the neurons, the connections between layers, and then all the parameters, which we haven't talked about yet. Basically, all of these are different questions. So if you think back to whenever we looked at some of the decision trees, and we looked at all of the options that we did not fill in, like the number of leaves and the number of layers, for most of those algorithms, we had 5 to 10 options that we could have filled in that we didn't. These are the same kinds of things, this stuff that we see here under hyperparameters. Those are the same kinds of things, but for a neural network. And so just like you have to select the kernel for support vector machines, we have to select the initialization function for a neural network. Some of these, just like with what we did last week, have been automatically guessed at by the framework that we're going to use based on best practice. But in a lot of cases, it takes a lot more art and some science to build a really good neural network. So there's a huge amount of research being done in this area as to what is the best initialization function, what is the best network architecture, but it's still a lot of trial and error for most machine learning practitioners. So we're going to break some of these down and talk about what they are and what some of the choices are. We won't cover everything here, and you definitely won't be tested on everything. Hyperparameters basically just mean the parameters for the model. They're the things that we set on the model that influences its design, the math it uses, and its complexity, things like that. And so different parameters can yield significantly different results, and that's why machine learning, deep learning experts are highly coveted at the biggest technology companies right now, is because this work is not routine, and it takes a lot of experience to get really good at. All right, so let's talk about some of these and unpack some of this stuff. So the key neural network types. So this is, whenever I said architecture, these are the big high-level neural network architectures or types. So we have dense, which we've basically already seen. So it uses standard neurons like the LTUs that we talked about, the linear threshold units. Those are just standard neurons. They're just, we put weights in, it sums the weights, and it applies an algorithm. And they're densely connected. So everything is connected to each layer before it and each layer after it. And so that's a dense network. It's this right here is a dense network, right? Everything on the input layer is connected to the hidden layer. Everything on the hidden layer is connected to the output layer, and then these outputs are actually our guesses. So this is a dense network. Dense because of how many interconnections there are between the layers and the inputs and the outputs. We also have a different kind called convolutional neural networks, and so these are frequently used for image recognition. They aggregate the inputs, and so with images tend to be a lot larger than other input types. So if we have a 299 by 299 pixel image, that's pretty small, right? But that's a pretty small image, but it's still 89,401 inputs or features. So if we have something that's only 299 pixels by 299, for a neural network or for any machine learning algorithm, that's functionally almost 90,000 inputs or 90,000 features, which means even that small image is already very wide. And then we have to multiply that by 3 because each of the color channels, red, green, and blue, get their own levels. And so basically we have to have a network for every one of those color channels too. And so all of a sudden we're talking about 268,000 features or inputs for our color image. It's only 299 by 299 pixels. And so dense neural networks tend to run out of memory or run very slowly because everything is connected to everything, and we've got 299,000 of these X's, right? We'd have 299,000 of these right here, or 260-some thousand of these right here. And so that's a lot of connections from this layer to this layer for the network to manage, and you tend to run out of memory on your computer. So we have a different kind of network that's not densely connected called a convolutional that handles that by basically it reduces the input and it shrinks the image as it goes from layer to layer. And we'll talk a little bit about that. Recurrent neural networks identify time series or sequential patterns in data sets. So these basically look for changes over time from your inputs, and what they do what's called back propagation through time, or they unroll time series inputs to look at how things step from one time step to another. And then we're not going to talk about it any, but there are adversarial neural networks which are unsupervised, and they attempt to encode and decode data to model features of the input. So this is commonly used for like faking images. You basically have two networks, one that generates fake images and one that tries to detect if an image is fake or not. And you pair those up, and basically they constantly try to exceed each other. And if the network is constructed properly, that's how some videos now, solutions like deep fakes are coming to light, where famous people, famous politicians, there are videos that have been made by neural networks of them saying ridiculous things. The quality is still very poor for this kind of output, but in the next few years it will probably improve dramatically and concerningly. But at the end of the day, adversarial networks can be used for a few different things. That's just the easiest to sort of discuss and see in practice. So let's talk a little bit more about convolutional neural networks. So these networks are modeled on the architecture of the visual cortex. So vision is made up of overlapping local receptive fields, which together form an image. So what this really means is, if we think about this right here as an image, this is 1, 2, 3, 4, 5 pixels by 5 pixels. This is a 5 by 5 image, so a very small image. And what happens with a convolutional neural network is it looks at a few pixels at a time. In this case, you can see it's looking at 9 pixels at a time. And it takes all 9 of those and it turns it into one value here. And so usually what it's looking for is a gradient. Like, did I experience an edge anywhere here, like where the colors go from white to black? And if so, then it puts a value up here like a 1. And what it really represents is key features or parts of images, like the boundaries of a number for a handwritten number set, or the boundaries of a vehicle or a stop sign, basically where an image changes from one color, from one contrast to another. something like that. But the critical thing here is we take this image that's reasonably large and we shrink it, and then shrink it again in this case. And so these are configurable parameters that I don't know that we'll get into very much, but it's called the stride, which is how many pixels at a time your neural network looks at. And intuitively, you would think that more would be better because it'd see more at a time. But at the end of the day, most researchers have found that using a 3 by 3 stride or area like this, looking at 3 pixels by 3 pixels at a time, tends to be the best. And you just add more layers to make a better network rather than looking at more pixels at a time. So at the end of the day, the really important thing to think about here is this neural network functionally looks at sections of an image. And once it looks at this section right here that we've seen, it moves down 1 pixel and it looks at these pixels immediately underneath, and then it moves down again and looks at these last 9 pixels. And then once it's done that, it moves over 1 and it looks at these middle, and then down, and then down, and then over, and down, and down. And there are more sophisticated things that can be done if this image, for example, is not regularly sized. What do you get, if you have one more layer here, an odd number of pixels? We can do things like padding the image so that it has an even number of rows and columns for our network, but that's not in scope for this. So at the end of the day, these layers are not fully connected because you can see here this is very large, this is smaller, and this is smaller, and these pixels right here, or these the neurons that represent them, have no relationship to this one right here, right? So these layers are not all connected to each other. Instead, it takes a little bit of the image and it compresses it basically, and it takes another piece of the image and it compresses it, and takes another piece and it compresses it. And so we can look at rather large images this way without running out of memory. So recurrent neural networks are fairly complex, and we're not going to use them. So if this section doesn't make any sense, it's fine. It's not going to be on the test. We're not going to implement a recurrent neural network. But for folks who are interested, I'll talk through it. And so these networks maintain state across steps. So they recognize patterns in sequential data. Sequential data is usually time series data, like heart rate data or like stock data or like any kind of sensor temperature reading, where we see, we get readings every second or every 5 seconds or every minute with some consistency. We can take each of those readings and feed them into this type of neural network, and it will start to see the changes over time, and it will understand that maybe whenever the heart rate increases by a certain percentage for a certain period of time and has a specific pattern, it's, whatever, an arrhythmia or something. And so these kinds of algorithms can detect sophisticated patterns across multiple different features that are all time linked. And it does this by taking in, it takes in the time series data, it feeds it through the algorithm. So this is like a more sophisticated version of that LTU that we talked about a couple slides ago, right? It takes the input, it applies an equation to it, and it gives an output. But it doesn't just send the output, it also sends itself a reading that's its own weight, basically, for the next input. And so if this is at the first second, and it runs through the algorithm and produces a prediction about whether this patient has an arrhythmia, it also says, here's a feature to send into the future, to send into the next second, and then into the next second, and into the next second, and so on.